Hello, welcome to another module in this massive open online course. So, we are looking at compressive sensing, and we have seen that the cost function for the compressive sensing problem, that is minimizing the L0 norm, is highly non-convex, and therefore, we have to invent or come up with intelligent techniques to solve this thing, and in this module we are going to look at one such technique which is termed as the orthogonal matching pursuit. Okay. So, we want to start looking at one of the schemes for solving for sparse signal recovery. This is known as orthogonal matching pursuit. What happens, and this is also abbreviated as OMP. Remember, the genesis of this problem is something like this. We want to enforce the sparsity, that is, we want to minimize the number of non-zero entries given by the L0 norm subject to the constraint y bar equals phi x bar, but this is non-convex. So, we want to come up with a scheme to solve this, and that particular scheme is OMP, orthogonal matching pursuit. What happens in orthogonal matching pursuit? You write this matrix phi as a set of columns, its corresponding columns. Okay. So, you have phi 1 tilde, phi 2 tilde. Remember, each is a column. Okay. So, the set of columns are since we call the rows as phi 1 bar, I am calling the columns as phi 1 tilde, phi 2 tilde. Since this is a m cross n matrix, there are n columns. Okay. So, this is phi n tilde times x1, x2 up to xn, and so these are n columns, of the matrix phi. Now, the orthogonal matching pursuit, remember the name itself implies matching, alright. So, you are looking for something that matches. Okay. What is the thing that matches? You are looking for the column that closely matches the vector x bar, which means basically you have to find the projection of x bar on each of these columns of, you have to find the projection of y bar on each of these columns of the matrix phi and choose the one that has the maximum. So, you are basically trying to find which of these columns is probably there in the linear combination, alright, and therefore, you try to find the one which closely matches y bar, which means basically the column which has the largest projection on y bar, or the column which basically yields the largest projection of y bar. So, the way to do that is, so we find the column of phi find the column that has largest correlation or basically projection with y bar. So, the way to do that is, we have I1 equals at the first stage. What we do at the first stage is basically we choose I1, the index 1 amongst all the j columns. Let me write it clearly as the one that maximizes the as a column j. You look at all the columns phi tilde j, take the projection phi tilde j transpose y bar, and choose the one that has the maximum projection. So, choose the one, right, choose choose the column J that has the maximum projection. Okay. And now what we do is we compute, we start building the basis matrix, that is A1, which basically comprises of this first column phi tilde of I1. Okay, so this is at this stage is a single column matrix. Okay, so this is A1. So we think of this as the basis matrix. This is, by the way, the first iteration of the algorithm. Okay. And now what we do is, given this basis matrix, we try to find the best estimate of the vector x bar. So we minimize. So it's like we are finding this basis, all right. This is the basis for the linear combination A1, and now we are trying to minimize the least squares norm such that you find the best vector x bar 1 in the first iteration that minimizes this error corresponding to y bar, and therefore the estimate x hat 1 corresponding to our basis A1 is given as A1 transpose A1 inverse A1 transpose y bar. This is basically the first iteration. Okay, so what you are doing is you are trying to estimate the basis, okay, that is estimate the columns of phi which are present in the linear combination to give rise to, remember, only few elements of x bar are non-zero, which means only a few columns of phi are present in the linear combination. So which are those columns? That is what we are trying to find by this orthogonal matching pursuit. So we are taking the projection of each column on y bar, finding the one that has the maximum projection, choosing that column as the basis, then finding the best approximation to the y bar based on that basis. That is what we are doing here by solving this least squares problem. Now what we find is, we find the residue that is left after getting this best possible approximation. So the residue, so this is basically estimate of x bar in, remember, but first iteration. In terms of the basis A1. Okay. And now the residue after the first iteration, that is after your approximation, that is, remember, y bar minus the basis times x hat of 1. That is basically you have estimated x hat of 1, whatever is remaining, that is y bar minus the basis times x hat of 1. This is your residue after the first iteration. Okay, so this is the first iteration, okay, in the orthogonal matching pursuit. What do we do in the second iteration? Now in the second iteration, now we start, so this completes the first iteration. Now let us do the second iteration. Okay, I hope this is clear. In the second iteration, we do something very simple. We take the projection of this on the residue. So we find the column which has the maximum projection on the residue after the first iteration. So, what we are doing here, and this is the key step, find column phi tilde j that has the largest projection on residue R1 after the first iteration. So, after the first iteration you are left with the residue R1. Okay, this still has to be approximated. So, you find the projection of each column of phi on this residue and choose the column which now has the maximum projection on this residue. That is what we are doing, that is your index I2. Now, you augment your basis matrix. Your basis matrix now becomes, previously you have, remember, you have a 1 column matrix phi tilde I1. Now, you augment it with phi tilde I2. Okay. So, you are augmenting the basis matrix A2. You are augmenting this with the column phi tilde I2. Once again you find the best estimate x bar via least squares. Now, again you find, you have the basis matrix, you find the best estimate of x bar at the second iteration, the least squares estimate x hat 2, that will be given as A2 transpose, we know the least squares procedure, A2 transpose A2 inverse A2 transpose. So, what is this x hat? This is the estimate of x, best estimate of x hat 2 x bar best estimate of x bar in the second iteration. Now, you find the residue R bar 2, which is y bar minus the basics matrix times S hat. And what is this? This is the residue after the second iteration. This is the residue after the second iteration, and then subsequently, now what you do in the third iteration, take this residue, find again the projection of each column of the matrix phi, choose the one that maximizes, that has the maximum projection, alright, expand your basis or augment the basis, least squares estimate, alright, find the residue and progress, alright. So, keep repeating this process by projecting at each iteration. Start by projecting the residue from the previous iteration onto each column of phi, choose the one that maximizes, choose the one that has a maximum projection, and then repeat the process. Okay. So, repeat process. By carrying over residue to the next stage. So, each stage the residue carries over to the next stage. Now, till when to the do you repeat? Repeat. There can be several criteria. For instance, you might have a fixed number of iterations, or typically you repeat until this residue, the difference between the residue, that is the residue stops decreasing, that is you repeat until such stage that your residue, that is, let us say you have k iterations, that is, this epsilon is some threshold. So, what we are saying is repeat until the difference between residues is smaller than epsilon, residue does not decrease any further. Okay. Difference between residues in successive iterations is less than or equal to epsilon, that is, the residue does not decrease any, the epsilon is the threshold. This is termed as the stopping criteria. Every iterative algorithm you have to choose a suitable stopping criteria. Okay. So, this is termed as the a stopping criterion. There can be many stopping criteria. For instance, you can have a fixed number of iterations, residue until there is difference between the successive residues. You can iterate until the difference between the residue stops decreasing any further, that is, the difference between the successive residues is less than some predefined quantity epsilon, or so on. There can be various different stopping criteria. And now, after the stopping criterion, let us say you stop after k iterations. Okay. X hat. So, you have after k iterations you have x hat k. Which means you have basically obtained a fairly good estimate of approximation to y bar, and the residue is not decreasing any further. After k iterations, let us say you have x hat k, and naturally if you look at x hat k, that will have elements. Remember, after k iterations the augmented matrix is of size, has k columns. So, you will have x hat 1, you will have the estimated vector has k elements, x hat 1, x hat 2 up to x hat k. But remember, these correspond to columns. For instance, this corresponds to column phi tilde I 1, first one corresponds to column phi tilde I 1, second one corresponds to column phi tilde I 2, and last one corresponds to column phi tilde I k, and so on. And then therefore, how do you finally estimate the vector x? Now, x hat will simply be a vector that mostly contains zeros, except corresponding to the location I 1 you have x hat of 1, mostly zeros, corresponding to the location I 2 you have x hat 2. Okay. So, this is at location I 1, this is at location I 2, and the rest are zeros or rest zeros. Except your locations, these are known as the sparse locations, rest except I 1. So, we say except I 1, I 2, I k, rest are 0. So, this is a sparse vector basically. This is a sparse vector, and yeah. So, finally, to conclude, what we have is set x hat 1 x hat 2 up to x hat k at I1, I2, Ik respectively in x bar or in x hat, and rest of the entries of x hat are 0. Remember, all this is saying is basically through these various iterations you have estimated the basis columns, okay, which are phi tilde I1, phi tilde I2 at the second iteration, so on until at the kth iteration you get phi tilde Ik, which gives you the k largest projection on the residue, at the kth iteration, you can say that, okay. And therefore, what you have is basically you have this set of columns phi tilde I1, phi tilde I2, phi tilde Ik, and therefore the x hat vector that you estimate naturally will have k entries, okay, x hat 1, x hat 2 up to x hat k. So each of these entries corresponds to that particular column, alright, and therefore in the original vector x bar you have to set these entries x hat 1, x hat 2, x hat k at the corresponding columns, that is I1, I2, Ik. Rest of the entries of x bar will be 0. That is what gives you the sparse vector x bar, alright. That is the vector that is estimated using the orthogonal matching procedure, okay. So it is a very simple algorithm, it is a very simple, it is a very intuitive, that is at each stage you are finding the column of phi which has the largest projection on the residue, on which the residue has the largest projection, okay. So that is what you are finding at each iteration, and you are expanding the basis, and at the same point once you have the basis you are trying to find the best vector x bar that minimizes the residue, and you are computing that residue, taking its projection in the next stage, next iteration, repeating the algorithm, alright. So we will stop here, we will look at an example in the subsequent module, but we will stop here. Thank you very much.